Hello to those watching. This is Project Team 21003, and the project that we were assigned with, which is to motorize an ultra microtome stage for our sponsor, Reader's Trucks from RMC Bohacklet, which is located in Tucson. Starting from the top left, the team is made up of me, Avery Zhao, a biomedical engineer, Sarah Gilliam, who is also a biomedical engineer, Offman Algaham, who is an industrial engineer. In the next row, we have Diego Resendez, a mechanical engineer, Gazwan Muhabis, an industrial engineer, and finally Nick Ramos, who is our electrical and computer engineer. In this slide, you can see the general overview of our presentation. If you are interested, you can pause at this slide. For those of you who do not know what an ultramicrotome is, it is a device that allows the user to cut a sample on the nanoscale to examine it with an electron microscope. To add on, the sample does not need to be a biological specimen, but can range from all sorts of things. It simply depends on who uses it and what they need to cut to examine. The electron microscope uses a beam of electrons to magnify the sample for high-resolution images using the electron's wave-like characteristics. Shown in the bottom right is RMC Bohacklet's current ultramicrotome's design. Their current design uses manual translation of stages to align the diamond life on the upper stage with the sample. The purpose of our project is to motorize the lower stage, which will allow the users to move the stage at high precisions. This change was deemed to be necessary with Lycas, who is a rival microtome company, release of a motorized ultramicrotome, which has shown to be more popular than non-motorized versions. Next, I'll pass it to Nick.
Thank you, Avery. On this slide, we have the objectives and approach. The main objective for Team 21003 was to design, build, and verify a motorized ultramicrotome stage to replace the manually adjustable one with higher precision movements through automation, which is accomplished through stepper motors in X and Y directions. In order to reduce the cost and labor required to produce the new device, the frame of the ultramicrotome was mostly conserved. However, the main change that we made was making a hole at the side of the stage. Our approach was research different ultramicrotomes, Leicas and RMC Becklers, design different prototypes, create testing plans, and implement changes and modifications. Next slide, please. On this slide, we have our system block diagram, which is a rough overview of the mechanisms in the stage. On the far right, we have our controller, which is comprised of an Arduino, which is used to control the speed of the motors, toggle speeds, and prevent crashing through the use of our maximum travel system. The box beneath, connected by a dashed line, contains function prototypes related to the software. Our Y-axis movement and X-axis movement systems are comprised of 4 components: the carriage for the upper stage, lead screws, which you can get off the shelf, a stepper motor for the direction, and a microscope driver. If you'd like more details, you can feel free to pause the video and go over this. Now I'll pass it on to Gazwan.
Thank you, Nick. Okay, for the vacation table, the remote control, maximum y-axis, and the x-axis displacement movement assembly, and overall velocity of those stages, the limit value reference for the y-axis is 12 mm and 60 RPM, and for the x-axis is 25 mm and 60 RPM. Our reference value for the y-axis and the x-axis displacement, they are aided by the limit sensor, and they are all passed. Most of what we have in this table is passed, except 2 things. We recognize we currently have 2 BD under the pass or fail. The first one is the 2B environment operation temperature, and the second one is 5A performance accuracy. And the reason for this, it's because they could only be validated if the ARM existing system was integrated into the structure. Since this part is out of our scope, we might not receive the test results for it. So we have a TBD for now. So now we're gonna pass it to Diego.
As a part of our models and analysis, we calculated the maximum displacement and maximum velocity. We based our calculations using M6 by 1 mm pitch lead screws. In order for our stage to travel the maximum linear distance of 25 mm for the x-axis and 12 mm for the y-axis, the lead screws must have a maximum rotation of 25 and 12 revolutions. Our maximum velocity for the stage was determined to be 60 revolutions per minute. Next slide. Our team also analyzed the required torque to efficiently move the stage in order to determine the proper size of the stepper motor. We calculated the total torque by summing the running torque and the acceleration torque. We ended up with a running torque of 0 since friction was calculated within our acceleration torque, and gravity and external torques were neglected. By summing the total inertia of the system and multiplying by the change in speed over time times 2 pi radians, we obtained a total torque of 1.75 ounce-inches, which converts to 126 gram-centimeters. Next slide. Using the stepper motor torque curve and plotting our calculated required torque, we can see that the 126 gram-centimeters and a speed of 60 RPM, we are well below the stepper motor torque curve, which means we are within the operating limits of the stepper motors without stressing them or causing excessive wear and tear. Next slide. Here we have a 3D model of our ultramicrotome. The main components as shown in the left-hand side include the frame and top stage. The right diagrams show the main internal components of the driving mechanism, which include the stepper motor and lead screws, as well as limit sensors with detection flags to prevent over travel and damaging our system. I will now pass it over to Nick for the demonstration.
Thank you, Diego. On this slide, we have a video containing photos of our system, including sides of the controller and the stage, our PCB board, bottom of the stage, and a closer look at the motors.
This is the controller for our ultramicrotome stage. Down here we have 4 buttons. This one changes the speed to fast, indicated by a single blink from the yellow LED. This button changes our speed to slow, as indicated by 2 blinks. This button saves the position of our stage, and this button will return our stage to home. The save is indicated by blinks from the green LED. Homing is indicated by a single blink from the green LED. These buttons form our compass rose that we will use to move the stage in the corresponding directions. Change to fast, north. This red LED flashed when you hit your maximum and prevents the stage from moving further. South, east, and west. We've reached our limit, doesn't move. Let's return to home.
That's the end of the video. Now I'll pass it to Hoffman.
Thank you, Nick. We've encountered many surprises during our senior design project, first of which, you can never have enough research. We have thoroughly researched different ultramicrotomes and parts that we may or may not need for our lower stage and controller. Second is the extent of COVID-19 affecting our project. We've faced some delays with our ordered parts and machining. And finally, it was a challenge and time-consuming process to fit all components into the lower stage and controller. We've learned 2 important lessons, which are always having a timeline and abide by it because it helped us focus and realize our goals. And finally, to always have a backup plan that helped us tremendously with the unexpected problem with machining. We had to outsource to a third-party workshop. Next slide. For our conclusion, the motorized ultramicrotome has met all major requirements set by the sponsor by changing the software for the controller, and the velocity with acceleration of the stage can be altered by the user for better control. Like its predecessor, the ultramicrotome gives the user 2 different speeds and make adjustments. And finally, we replaced the fine coarse lead screws and standard lead screws to have it more cost effective. Moving on to the next slide. We'd like to thank our college mentor, Patrick Cadwell, and our sponsor mentors in RMC Bookler, who are Dr. Greg Beggar, Greg Fries, Mike Leeper, and Peter Slugs. Thank you.